Today we'll cover more in detail about one of the indexing structures. One is ISA, two structures, and the other one would be. Okay, so index sequential access method. This is. I mean, this is not algorithms course, so we won't be delving deeper into how they implement it, but we'll certainly see how they work around it. But the idea that you want to take home from today's lecture is these are the two data structures that are being used. B plus trees is extensively used for indexing. And what it is doing is this lecture actually expands on if you have, this is your record. And remember, we made the index here and some kind of mapping we did. So we are going to expand on this part. How you want to organize your index so you can do your search faster. Okay. So let's look at ISA. So ideally an index would be so there will be a pointer P0, then there will be P1, K1, P2, K2, and going on. So what we have here, these are representing the keys, and these are the pointers to the records which follow. So if we were doing it on salary, value of the key may be 20 here, and this pointer will then point to the record which corresponds to this key. So then this is our index. Okay, and if this index is built like this, what is happening is this is where is our record. So if this record is very big, your index also ends up becoming big. But the advantage is that this may have a lot more fields than your index. So that's why you gain performance here over this. Now the question came, how do you improve the performance if this becomes really large? So now let's start looking at the index itself.
Say when I was reading the book, you know, I mean, the thing comes up like, okay, you know, we know kind of going through the records and looking, you know, that the index seems like a huge advantage over that. And then just it seems like, gee, with modern computers, to make it really an issue to have searching through an index be a big overhead item. I mean, can you tell me practically, is that still the case?
Yeah,
it is.
It is. It is. Think of a database of 1 million lines of data with 20 fields. And this is real. This is a small data which I know one of the projects was working on with.
Okay.
And it just, my only problem is I can't give you an example in which the indexing, because the problem we did when we joined AD, there was a problem that everybody got trained for 2 weeks on actual rigorous coding, doing performance enhancement on queries, doing data import, Perl data scrubbing. And that is when we imported this database, example database, which had 1 million lines, which had corrupted data. So when you do a data import, you have to make sure when you insert in your field, you don't break your integrity of your data set, otherwise it won't insert.
But the import, you can kind of, I mean, that's a one-time thing where
right.
You can take all the time you want to make
exactly.
Sure you get it right.
So what we did after we did the import is when we started looking at the queries to access, prepare reports out of it. and if you don't have indexes, it was like it would take several seconds to do it, one report. And with indexes, you can come down to milliseconds.
Okay, now.
That's not his question.
Yeah, so the question is, okay, I can understand that advantage.
Oh, okay.
seems
I thought-
intuitive enough. But now, like to start worrying about the indexes, like for this one, just based on very crude ideas I had with indexes, you make 20 different binary trees on each of the fields, so anybody does a search, bing, you've got it. And it's, okay, maybe it takes a while to create those trees, but again, you can let that run during downtime, so to speak. So, but now you're saying that it actually makes a difference, the indexing scheme, in terms of
Performance. Maybe I totally misunderstood your question. I'm sorry. Can you rephrase it, because I just went totally sideways, that means.
Okay, so there's a bunch of different, we're talking about different indexing schemes
Yeah.
here.
Okay. Yeah, you're right.
And it just seems that having an index is, like that
Improvement,
advantage you
right?
described before that makes sense.
Mhm.
You're looking through one table rather than
Yeah.
a zillion records. But it just seems, I don't know, just.
Does it really
Okay.
make that much of a difference what scheme you use for the
What
index if
index
there's
is
a
it?
small relative?
Well, some stuff would be like B trees. I don't think this is the right way, but whichever. Well, one of them is not good if you have a lot of records that have the same value, because it basically becomes flat again. So if you know something specific about your data, you know that.
Yeah, I guess
I would-
intuitively thinking, yeah, if you're doing inserts and modifications,
Again, it comes down to the question of how the data is going to be used. Again, it always comes down to whether this data set, same, if there is, what type of data it is, whether it is mainly reads, whether it is a lot of updates. So then you want to, every scheme of indexing is solving one problem really well. And that is how they got evolved. So that is when you'll make that choice, whether for this kind of a data set, I'll be choosing this over this. Does that?
yeah, I can just tell. I've been implicitly thinking the whole time about just the pure finding problem, but not the updating problem. Yeah.
You'll see that in this ISAM, which is static, you don't. So the fundamental idea is that you define all the leaf nodes and the search nodes in the beginning.
Right.
Okay, and you don't delete the leaf nodes when you delete the data. So, and now if you go to the other one, which is say B plus trees, which are constantly making sure that they are balanced.
Right.
So in that you will have, so both of them will have their own advantages in one, and the other one is then suddenly you have these leaves which are empty.
Yeah, and I can see it also matters like, okay, you're doing a lot of updates during the day, so maybe, by the end of the day, this performance could have really degraded if you have the kind of indexing that, doesn't-
Going and then linking at the bottom, yeah.
But then at night, in downtime,
Go back.
redo the whole
Yeah.
thing, but maybe that's too late by then. Maybe you paid too big a penalty intraday.
Probably. You mean that at night reorganize it, then next day keep going that way? I don't know. Yeah. I have actually requested, I haven't asked, I have requested if we can get the somebody from our DBA group at AD to come, because I don't have something that I'm missing, which I really want you guys to get exposed to, is that the real work that a DBA does. I have gone through these problems as I was trying to solve something for a client, or as they came up in writing algorithms for my research. And that is how I'm taking courses along it. But I never actually sat and solved a DBA problem that somebody's database crashed and you had to get it back. That kind of thing would be a huge, I feel that if I had that, I would be able to give you so much more. And I've requested, I hope somebody can come even for 1 hour to actually sit with you guys, give you just another abstraction layer on top of why you are doing all this. So hopefully we'll get that, and then we can make a discussion out of it. Is that okay? Okay. So What were we talking about? Index, yes. Okay. So if this index is really large and it spans multiple pages, the binary search through this is sorted because it has a key which is sorted along with the record set. The binary search also becomes quite expensive. So what it started happening was they wanted to reduce it down even more when the final index can be fit into one page. Okay, so you will start from this, so I'll draw it, otherwise it will become confusing. I don't. Oh, here. So here are our pages of data. Okay. Then this was our first index, and just for depiction point, let this be spanning 3 pages. And these will point to the first entry here. First entry here. Oh, sorry. Okay, and I'll make it simpler if we make it 4 here. And then we make an index on top of this. Oops, sorry. And finally, you have this index, which is only 1 page, and you can get to everything below it.
So why are these things divided in 2?
This is just depiction. I'm just thinking that each page can only take 2 pointers in it, just because I can't, as a depiction point only. And I have kept it consistent just so that we know that this represents 1 page.
So everything's on one page, but
To start off with.
in order to get to some actual
Leaf
data, you
here,
have to
yeah,
go
leaf
through
here.
however deep
Exactly.
it is.
Yeah.
Number of pages.
Yeah.
I'm a little unclear here. What's being indexed?
Okay. No, excuse me? I'll put in some numbers so that it'll become clearer. Okay. So there is, this data has key, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Special pointers?
No, these are the key values in here.
Okay, but aren't they interspersed with pointers to?
Yeah, to the data, to the real data. I just want to draw this leaf node because, yeah, you're right.
The real data.
Right. And then this is the pointer here. So this pointer will be, say, P1 or whatever it is. And because P0 will be somewhere here to start off with. And 1, then there'll be P2, which will be 3. Okay, this key value is 3 here. Okay. Then you go up here, say this is say, another pointer P prime, which will take 1 here. Okay. Then there is a pointer here, which will take 1 here.
Where's the second one in the second to top left?
Which one? This one?
Yeah.
This one. This one is going to point to 5 here.
And that'll be 5 in the right-hand box there, and that.
7. Because these are also having their own pointers pointing down, right?
Right. But the one next up.
This one, yeah,
5.
you're right. Okay, because what you see is here, if something is between 1 and 5, it has to go on this side. Let me just put the number here. So this would be, here would be 13. Is that correct? and this would be 9. Please stop me if I make a mistake somewhere, otherwise everybody will get confused. Oh, sorry. I'm sorry. Okay.
Realistically, could something wouldn't be between, because these are the way these are sorted, something wouldn't be between 1 and 5 and be below 1.
No, they won't be. See, try to,
like the 4 would be
because they are sorted.
5.
They are sorted. That's why. If you want to get to 4, you'll follow this tree, then again follow here, right?
But
then because it is bigger than 3, so you'll come here.
They're not necessarily sorted on those records, but the pointers then go wherever they need to go. Right.
Ask me. I may be able to explain it more if you want to know.
it seems to me that when this was being built, the numbers wouldn't be laid out in that structure. That the 4 that's at the very bottom would be next to the 5
Where
on
next
the
to?
second row.
Why would it be next to
No,
5?
second row from the top.
Oh, here.
Or because it's not going to be between 1 and 5. It's going to be less than 1 or greater than 5.
No. It is going to be, so what you are seeing here is anything 5 or more is going to follow this pointer.
Okay.
Anything greater than 1 or greater than 1, less than 5 is going to be this side.
So we just arbitrarily say that the leftmost gets the cluster of everything less than up to the next one?
Yeah. And it gets everything up, but we split it here, so it can't get anything beyond 8. Because for 9 onwards, you split here.
Okay.
So both of them get clustered with the delimiters coming from top.
Okay, I guess I just don't like the asymmetry of it, but that's just...
When you insert something, you have to rebuild the aesthetics.
Okay, that is another. So that is the next thing. So with this, so we defined, say, this tree. So now his question was, we can talk about it later also. Well, what we'll do is we'll pick up an example and we'll go through it again after the lecture. Okay. What was your question? Insert. Now, if something is to be inserted, it is going to come on the leaf nodes, and then you have to create another page for it because there is no space. Okay, so this is how you generate the linked pages here to do the inserts. The problem with this is when you delete this one, let us assume. You just leave it blank. So there are a lot of blank spaces, the thing that you mentioned, that if things keep on changing during the day. But if things move out of here, so I'll give you an example.
So an insert adds layers.
Yeah, if nothing is empty. If there is something empty, then it will insert it.
It doesn't get bushy though, it just goes straight down.
Yeah, because you have to follow that hierarchy where it is going to be in that range. Let us look at this. You could actually have deleted this, but 5 will stay up here. So what is going to happen is you requested 5. Your search wanted number 5, for an example. So it is going to keep following, and then it will hit here and it won't find it, because the data has to fall here. Okay, so it will return that not found.
So it's inefficient in the sense that it doesn't detect that until it comes.
Absolutely.
So before that insert was made and that bottom
This one? Yeah.
box was added, that bottom row of keys actually have pointers to data. Right?
You're right, yeah.
So in order to insert another set of key pointers, you have to move that pointer.
Your pointer is not
Yeah.
moving here, because this is still pointing to, so when you do this, you'll insert a new pointer, right? When you added a new data, right? So you will have a new pointer to the new data that you added.
So the 5 box there
Mm-hmm.
used to have down below the very bottom. And I used to have a pointer attached to it that went to the 5.
Right.
So now we're replacing that pointer no longer points to the data. It now points to our new box.
No, that is not. No. It is not being replaced by that because you could still have this, right? This pointer will go to data still.
Okay.
All this is telling you is that it is going to fall in this tree to look for it.
But how it follows the tree by these pointers, right?
Yeah.
So it can
No, this
5 can have 2 pointers, one to the data, one to another set of keys.
it is linked here. I should say.
They're separate. The two
This
concepts
is
of
another
pointers are
page.
separate.
This is another page that is added in here. So for the matter of this search, this is not like another level is down here.
Oh, okay.
For this level, you can think of it as another page appended here.
And okay, so
I kept this representation because book is using it.
okay.
It confused me also initially
But it's
that you are
not
actually
like-
adding a new layer, but there is nothing below leaves.
Okay, and what points to it? How would you get to that section?
Which one?
That new one, if that new one that you added.
So this page, so now because I made it all complete sequence, for instance, let there be 6.5, okay, which is going to be here because it is less than 5. So if it is 6.5, it is going to follow here and find it.
Just like a linked list.
There is another page attached to this leaf.
Okay, so the same pointer, the 5, that brought it to the 5.
Yeah, is going
pair
to
now
is going to
bringing
take it
4,
2 pages.
a 3, a 2.
Yeah,
two-
four. You can say 4 entities.
Okay.
So this is good for inserts.
This is
As you keep inserting, once you make it down here, you're then just doing a linear search through whatever's there. And that's, so you want to minimize that.
And these root sections that is longer than a page.
excuse me.
The base. The base set
This
of
one.
pointers end up longer than a single page with inserts, right?
Yeah, you can have.
Okay.
Now after you asked me the question, I am now thinking, what is going to happen if we get rid of this? What happens to this pointer? You know what I'm thinking is that somebody deleted the data. Okay, this is our data, and this was 5 key pointing here. Now we deleted this 5, and this also went away.
But there's still
Somewhere.
For that 5 to point to get to 6, 7, and 8.
No, that is not a problem because 5 is not going to point to these. This point is taken care of. What I am thinking is, so if we insert 7 or 6.5 here, or 6.2, which goes in here, because that is what is confusing me now. I read it in the book that when there is an empty, you can insert in there. So how will you reassign this pointer? You understand what I'm saying? That one is oh no, I think you can. That's fine because it is just an address. No, that's fine. It's fine because all you're doing is you are giving it the address, so it'll work. Sorry. It clarified my brain. Okay. But this part is clear now? Okay.
So this is the index record, if you will.
Absolutely. This is how you should actually think.
And this is a tree of pointers of which the bottom one, all the upper levels are pointers to further pointers.
All these are index entries till you reach the leaf node.
Which is got a lot of use.
It is pointers to data. That is the only difference. Okay, this is helping us sort. This is helping us point.
Is there a SQL command that does this? When you just create an index?
What I'm wondering is, I think we can specify the type of index that you want to build. Can you check in the book? Do they specify something like this?
How many choices are there?
I think B tree is the most commonly implemented.
They have some create index commands. I'm not sure if it's SQL per se.
It could be basically, it could be SQL, but then Oracle may have its own syntax. It may, Postgres may have.
So to choice between this and the B plus tree and this B plus tree.
Okay.
So originally that bottom index, what inspired this whole tree structure in the first place was that bottom index was all just one set of sequential pages, right? And that made it kind of hard to get through.
No, not hard to get through, but when you're doing a search on a huge one set of indexes, you're doing a binary search because it is ordered.
Yeah.
So with very long indexes, the overhead is very high. You want to break it up into smaller, that binary search you have to do in less number of entities. That is the idea that prompted this, that okay, let us, before we actually hit the binary search on the leaf nodes, let's try to classify or qualify more before we hit it.
Doesn't this just model a binary search? In a sense, like it's like you guess the middle and you find out whether it's.
Yeah, it is in a way.
You guess and
You can think of it as parsing the binary tree.
like this takes log n steps, just like a.
Exactly.
binary search,
So
right?
from log n, depending on how many steps you have.
Okay.
Okay.
So how is it
Not
faster
log
than
base
doing
2.
binary
No, that is
search?
base 2. That is log base 2.
Okay.
This one is as many levels you will have, the base will increase. So you'll get much smaller time.
Okay.
Yeah, you only have to load the pages. It's meaningless here because this is a binary tree, but presumably.
Yeah, it's a wrong example.
So,
It's actually an binary tree.
On each page, right?
yeah.
This log yourself. Right.
So that's very different.
Each one of these is like that.
How does this work if you have on the page that starts with 5 as the value? If the next value under that was 7,
Which one?
no, one level up.
Here?
Yeah, so you have a page, and the first value on the page is a 5,
Okay.
right? What if like the second value on the page was a 7, and you on the same page, and you were doing a search for everything that was equal to 7? How do you?
On the same page, you won't have the number 7.
Okay.
Because these are, this is the first value of the next page.
So it has to be.
Exactly.
Okay. So if you only had one value on the page that, if you had that on the page that started with 5, all you had was one value, 5, and your next value was 7, you just have to start that on the next page, and you
So-
just have a page with just one record. I guess.
That is a very, much bigger a leap in thinking, but think of it like this, that you will have, if there are 10 rows in this page, or records, and another 10 in this one, whatever the first value is going to be here these are the key values that will go in here. I just took an example because it was easy to write a sequence like this. I should have actually done 1, 10, 20, 30, so that you know that in each page the first value was 1 that went in, and then 1 will go here, and 10 will go here, 20 will go to the next one.
Okay, but you still have to break it up so that you don't.
Always the first page, because that is what will tell you that which page to go to find it.
And then this subsumes away the choice of having to decide which field to index on in the first place.
Fine.
So if we delete something, the pointer gets deleted, but the index entries stay the same.
The top one will, that's what the example of 5 we took. That if you delete 5 from the leaf, it will stay here, and if you're looking for 5, it will come and tell you it didn't find it. Okay. So in terms of inserting that we brought up, that is called overflow, because then you have to add more pages after you have already defined your tree. B trees, or B plus trees, I should not say B trees because it is another type of tree. And B plus trees overcome this by dynamically rearranging themselves. That is the power of B plus trees and keeping their balance, not having empty slots or pages or indexes.
What's the difference between these trees and these class trees?
Okay, B trees is left, right, left, right, left, right. In this, what you have is you have the tree structure, but as many branches as you can, because these are pointers.
Okay. So instead of being limited to only two.
I'm sorry?
Instead of being limited to only two branches from each node, you've got.
As many as, yeah, because these are pointers. These are pointers.
stands for binary?
I don't know. I won't say that. Alex can turn off the tape, because this thing has really, really taken my brain off. I mean, yesterday night I was trying to qualify the term B, and I was looking into my algorithms books. I pulled out my data structures book, and it is almost like full stop. They use it so many times in so many different forms, but I don't know what to say to that. But I will not either way.
So this,
It is a type of tree. That is.
All right.
It's not the A tree or the C tree.
It might be balanced.
Next would be B question mark tree.
so the trouble,
It might be balanced because you rebalance it.
That could be it. Ho ho ho! Turn the camera.
What's the plus then? Then what's the plus then?
Balance better.
hey, it worked for the C language, why not try it for the B? So with ISAM, if you have lots of inserts, then on the bottom level, you're getting just a gross point-by-point comparison. That's what it converges to.
Exactly. And so at some time you have to do the reorganization that you talked about, if you want to stick to that structure.
But this one's going to rebalance every time you do something. So
Yeah.
It's going to take time to.
I don't know if I would say it'll take time to do that. I'm trying to think. I'm trying to think of the operation. I'm thinking in terms of the operation that will go into it. So what we will do is we'll be moving the pointers. Effectively, we are moving the pointers. Right? That should be, because you are just changing the address. Because you're not, what I started thinking is, are you going back and writing to the disk? That is where our time would get eaten up. But I would like to check that also, if you can check also. My feeling is because all you're doing is reallocating the pointers. That is all you're doing. When
You have
you,
to write that to the disk sooner or later.
okay. Okay. I'll want to take the example of the book itself. Okay. What happened?
This guy was coming with the phones. He's just been going back and forth the whole time.
Yeah, like stacks of 5 phones at a time, and he's made at least 5.
Okay. Let's look at the B tree. I'll take the example that is in the book. What kind of discussions are you guys having in the, yesterday there was no recitation. What kind of discussions are you guys having in the recitation? Are they okay in terms of examples? Is that just go over the examples and
And regarding the SQL quiz that we had, Rusty told me that it'll be good if we have a review of the solutions. Is that something that you guys want?
Yeah.
So we can use a recitation to,
Yeah.
and a quiz on Sunday.
This Sunday? Take home.
Take home?
Post it, so we can do it at home.
Do it at home? Okay.
But we're going to do our projects.
Quiz or
Yeah,
so no quiz? Again, I'm feeling there will be two successive weeks without a quiz.
But usually, I think of projects and quizzes as really mutually exclusive. You go the project route or you go the quiz route. Feels this
Very strong.
It's very unbalanced. 8 quiz plus tree.
Okay. U trees. So there will be no quiz on Sunday. Is that what is the?
I think we should take a vote. No
Everyone gets one vote, including the teacher? Is that
Me and Alex. Quiz.
You have to film it.
Okay. No, I also actually I had decided there will be no quiz so that you guys can actually think more about the projects. Really, then do a good job. Just justify your own time, really. And second is then I would use one of the lectures next week to give you guys a quiz. Okay? Because we should. I want to have at least enough objective evaluation to give out the grades. I don't want it to be subjective. That it should be something I can myself qualify. That's why. And we didn't have a quiz. We'll give you a lecture off, and we'll have a quiz during that lecture. And assignments, you'll get each other's assignments next week starting also. As soon as you guys submit the assignment, I mean the project deliverables, they'll be given to 3 people apart from you. You'll be
They're due like next week?
Monday. The ERD and this first deliverable.
Yeah, what's the next stage of the project?
Next stage would be if you already have all the SQL queries. I want to see what we get out of Monday, and then we'll decide what is the next step we should do. So that's it.
The query should be in relational
ER diagram, and the queries should be if you have queries, or at least you plan to write certain queries for the new tables or relations that you decided. Put them in whatever can be put into select and project, relational calculus, relational algebra.
Either one, relational algebra or relational diagrams?
No, both.
Both.
Same query in both. Whichever queries would be much simpler. Try to use as many joins as you can, because you'll understand more.
useless circular
Okay. Let's finish this example. In B trees.
Get out of explaining B trees.
Huh? Yeah, B trees.
Never feel.
and then get to join all the fields together.
Was that him again? Oh, or somebody got up, right? Yeah, that's what I was wondering. I said, oh. So let's put it to the first one. This would go here. 17 would go here. 24 would go here. 30 would go here. Okay. Anything more than 30 will be pointed there. Anything more than 24, more than 17, more than 13, less than 13. Okay. So we will do insert. Okay. Where is the insert? Just a second. So the example is to insert 8 into an example B tree. So you want to insert 8. So insert should come, 8 should come here. Okay? But this is full.
I'm sorry, I lost the
Yeah.
difference in the numbers in the first one.
Yeah.
So 13, how does it relate to the 2, 3, 5, 7?
Because anything that is less than 13 is going to point here.
And then the last one, the 30 and the 35?
Greater than 30.
Oh, okay, okay.
So the 2 pointers on the 2 sides.
Okay, I got it.
Okay? Now we want to insert 8. So 8 has to come into this set. Okay? So this should effectively become another important thing about the B tree is how many values or how many pointers and values, key value pairs it can hold. So if it is of order 2, it has to have between 2 and 4. So
In this case, the order is 4. So what is
no, it's 2.
what is the order exactly?
So the number, how much you can put in here. So if the order of this B tree is 2, okay, so the number of key value pairs, key pointer pairs, or key pointers pairs you can save in this is going to be between 2 and 4.
What determines the order? Is it the number of?
No, you define it. No, you define it. You define it
Okay.
of the B tree. The root can have between 1 and 4 then. Okay? Anything that is not a root can have only between 2 and 4. If it goes below 2, it has to be either merged with the siblings or moved up, because it can't have 1 if it is not a root. Okay, you want to, so this is a way to enforce at least 50% occupancy constraint.
So if it was order 3, it would be 3 to 6 or 3
Yeah,
to 9?
3 to 6, not square. Oh,
3 to 9, did you say? Or 3
no, 3 to 6, 2D.
6, okay, so
Yeah,
2.
3 to 6.
And that's the number of minimum occupied cells? Out
Minimum occupied is going to be D, whatever is the 2 or 3 that you say in these.
Right.
So we'll never have this here. Then we'll merge these two and give an appropriate number here.
What's that called?
Order?
D is the order.
Order.
And you purposely leave blank spaces at first, or not?
No.
Okay, it's just how sparse it can get before it merges.
Exactly. Okay? So we are inserting an 8. So it becomes this. Now it can't have more than 4. Okay? So we will pick up, say, the central value and break it up. So what we did was, so we'll break it up into 3. Where will the 5 go then? And this 5. And 5 should join here then, right? Yeah, 5 has to come here. Okay? Exactly. So we'll split that now. Okay?
So did it break on the middle one? Is that the idea?
We pick up, this is discretionary. You pick up the middle one so that it gets distributed evenly.
Okay.
It's not, I could not find even in my own old textbook that there is a rule to do this. I don't know, have you seen it as a rule in this, or it is actually the suggested way to do it?
Whatever you break it on, that's what you add.
You'll have to, because this is what will qualify. Remember, this is what is going to distinguish between the two, that where it should go out of the two.
So when you get it to 2D plus 1, you break 1 to D and 1 to D plus 1.
Yeah. Okay? Now this will be broken up, and 17 will go up. And you'll make the new root node.
Why does that one get broken up?
Oh, because then it becomes 5. Once you moved 5 up. So this is the difference when you do with ISAM and with B trees.
What made you pick 17 to go up?
Because again, the center one.
Oh, just the center.
Yeah. That you can keep the balance. Because if I take 13 up, again this is going to die.
Right, okay.
If I take 24 up, this is going to die.
Maybe it's going to shine.
Because it can't exist as single 1. It will be less than 2, right?
And then deleting that.
So it would be like the special case where you choose b equals 1. Does that degenerate to a binary tree?
Let's see. If d was equal to 1,
You only have one or
then it will become. Now, I don't know if I would call it as a binary tree still. You know, the idea of binary tree is, yeah.
Well, go ahead and answer his question.
To me, the binary tree is something in which you have a left node, right node, and the parent node is lying between the two. Right? That is why I would be.
right, yeah.
That is the only reason I won't call it. I won't.
The parent
Let's not. Yeah, yeah. That's why I'm saying that.
So if, say you insert 10 here, and so 10 fills up the second thing.
Then here,
page, yeah.
okay.
And then you deleted 3. So 3, so now that has to be combined, and so it's combined with the one next to it, which means that it's now
5.
So you have to split it up again.
Absolutely.
And you do all 3 of those things.
So
at the same
I think this is a very good example just to understand the same. Shall I just complete this and then we'll do your example also? I just want to get to the final state and then we'll do. Otherwise, it'll become very messy. And I don't write very clearly anyways. Okay, so let us break this one up into its 5 and 13 here. So this is interesting. You know, can you look at this figure? This doesn't look right now. Can you pull up this figure?
Yeah.
Why can 17 have 3 empty slots? No, in the book.
Because it's the root.
If it is the root, then it should not have.
It doesn't have a neighbor to combine with it. It's
No.
root, so.
Why is it showing you root with a pointer? That is what I'm trying to understand. If I just want to understand whether they mean it to be a root.
Yeah, I
They
think,
always have an arrow coming into the root.
Oh, that arrow to root.
yeah, and I think you
That's
have
just
to.
how you
That's
point
just
it into the
index
data structure.
It's
here.
the arrow from the
That is their.
Is
Is that what is their representative? Okay.
Points.
Okay.
That does seem like that would be a problem because we're restricted
So they don't
to,
use it in other places, I guess. Yeah, they use it in the
fill
previous.
be between
They say root.
D and 2D. And this is
See this one then.
D is 2.
No, this is fine because you have all filled up. That's fine. I think that's okay. I think it is basically a pointer to the data. Yeah. Yeah. It is not. It does not represent any connectivity to any. Yeah. Yeah.
By the root itself.
Sure. Okay.
But the
Let
root
me.
has the same restriction on only having minimum D.
No, minimum is 1 on root.
1.
Yeah.
For the root.
For root, it is only for the root. It is minimum is 1. Okay. Let me just finish this. Then we'll do. So we have 4. I'll delete these also.
Well, you can try carding this door. You pick the lock or you card it down. You pick the lock.
Did I do something wrong here? 1, 2, 3, 4, 5. How come I have 6?
I think in the book, the 513 covered the three left-hand bottom pages.
Oh, okay. Oh, yeah, this is going to come here, of course. No, this is 13, yeah. Yeah.
I think the guy with a broken telephone from a broken light bulb.
And I think that 27 should be a 24 because you're saying.
Is it 20? Yeah, you're right. Yeah, I wrote it wrong. It is 24. It is 24. Okay, and now the 17 will go up here. Okay, so this becomes our tree. You're coming to your question.
We were somewhere else.
Okay. What is it? Tell me.
Oh, nothing.
Okay. Alex, I want to give them this recorder because later on I want to hear it. Okay. Okay. Now let's come to your question. What was it?
So say add 10 there,
Mm-hmm.
and then delete 3 from that guy.
Okay. So we delete 3. So this becomes less than 2. So it merges with this. So we get 1. So 2, 5, 7, 8, 10. So 7 goes up. So 7 goes up, and we are left with 2, 5. Right?
So what happens to those?
So now this 7 will go up here.
In between, so
Exactly.
there's 3 things there now.
So now 7 will go up a level. Now so okay, so this
Is the 5 still up there? I mean, do we?
yeah, 5 will be on this side,
No, I
right?
mean 5 in the second row from the top, the 5, 7, 13. Since we've added 7, we still have 5.
No, we have this right here.
As long as it doesn't get too big up there, the 5 will stay. As long as we're not
What would be the reason to put?
okay.
You
So-
understand this?
Right, I thought the 2 and the 5 were coming out of the.
No, not they are being broken up into 2.
Well, let me go.
Just a second, just a minute. Let me think. Yes, I wrote it wrong. Just because I started thinking the 5 should be included in the next one. See, because the left one is less than the number.
Right.
5 should not be. I made a mistake in copying down from 3 to 5. I wrote it. So this is 3 also here.
What happens to that has 5 in it still?
Which one has 5?
The down, that still has 5 in it.
Where?
It has 5 elements.
Oh, yeah. So with 5 elements, this is going to now break here, and this will give rise to 2 of these, and 7 will move up here.
And 7 has to be in front of the 8.
Yeah, 7's also down on the lower one too.
Okay. Where it says 8, 10, we need to have 7.
7's in
7, yeah.
this too.
Okay.
Marvelous. Although, where did the 5 go? Don't we need the 5 down?
No, there was no 5 here. 5 is up here. I made a mistake in copying down from the previous one. Okay?
If the key is a string, that this doesn't in alphabetical order, all disorder.
I looked at an example. There is actually an example in the book, and it does that. that I think it is David and another name, it gives you an example of alphabetically sorting them.
So you have a hash function and a strange one.
Yeah, you can hash it also. Okay, I think I want to leave the delete for the recitation. It's a similar thing, but we'll have a discussion